Welcome, everyone, and it's great to be at the GopherCon in New York. I love the city very much. And I'm Filippo, and this is my annual performance review. We are going to talk about all of the stuff that we did during the past year. And when I say we, it doesn't mean just me. It means me, Roland Shoemaker, Daniel McCartney, Nicola Morino, and Damian Neal, and many, many others, both from the Go team and from the Go community that contribute to the cryptography libraries all the time. I used to do this work at Google. I now do it as an independent as part of and leading Geomis, but we'll talk about that later. When we talk about the Go cryptography standard libraries, we talk about all of those packages that you use to build secure applications. And that's what we make them for. We do it to provide you with encryption and hashes and protocols like TLS and SSH. So the main headlines of the past year. We shipped post-quantum key exchanges, which is something that you will not have to think about and will just be solved for you. We have sold FIPS 140, which some of you will not care about at all, and some of you will be very happy about, and exactly. And the thing I'm most proud of, we did all of this while keeping an excellent security track record, which we try our hardest to maintain year after year. So let's start from that. This is an update to something you've seen last year. It's the list of vulnerabilities in the Go cryptography packages. We don't assign a severity because it's really hard. So instead, they're graded on the Filippo happiness score. It goes shrug, oof, and ouch. And you can see how, as time goes by, time goes from bottom to the top, things have been getting better. People report more things, but they're generally more often shrugs than oofs, and there haven't been ouches. More specifically, we haven't had any oof since 2023. We didn't have any Go-specific oof since 2021. And when I say Go-specific, I mean, well, sometimes the protocol is broken. And as much as we want to also be ahead of that by limiting complexity, you know, sometimes there's nothing you can do about that. And we haven't had ouches since 2019. And I'm very happy about that. Thank you. But if this sounds a little informal, I understand why. So I'm also happy to report that we had the first security audit by a professional firm. And Trail of Bits looked at all of the nuts and bolts of the Go cryptography standard library. So we're talking about primitives, ciphers, hashes, assembly implementations. They didn't look at the protocols, which is, you know, a lot more code on top of that, but all of the foundational stuff. And I'm happy to say that they found nothing. All right. Two-of-a-kind t-shirts, me and Roland Shoemaker over there. Okay, so it is easy, though, to maintain a good security track record if you never add anything to the standard library. So let's talk about the code we did add instead. First of all, post-quantum key exchanges. Well, we talked about post-quantum last year, but as a very quick refresher, post-quantum cryptography is about the future. We are worried about quantum computers that might exist 5-50, it's a range, years from now, and that might break all of the asymmetrical encryption, so digital signatures and key exchanges. Post-quantum cryptography is about classical computers. It's cryptography that we can do now that resists future quantum computers. And post-quantum cryptography is fast, actually. If you were convinced that for some reason it was slow, that's a common misconception, but it is large, which means that we have to send a lot more bytes on the wire to get the same results. Now, we focused on post-quantum key exchange because the key exchange defends against the most impellent risk, which is that somebody might be recording connections today, keeping them saved on some storage for the next 5-50 years, and then use the future quantum computers to decrypt those sessions. So I'm happy to report that we now have MLChem, which is the post-quantum key exchange algorithm selected presented by the NIST competition, which was an international competition run in the open, where contributions were mostly from international researchers. And you can use it directly from the standard libraries, starting Go 24. But you're probably not going to do that. Instead, you're probably going to just use CryptoTLS, which by default now uses the hybrid of X25519 and MLChem for all connections with other systems that support that. Why hybrid? Because this is new cryptography. So we are still a little worried that somebody might break it. There was one that looked very good and had like very small ciphertext, and we were all like, yes, yes, that's good, that's good. And then somebody broke it on a laptop. It was very annoying. So, you know, fairly confident in lattices. We think this is the good one. But still, we are taking both the old stuff and the new stuff, hashing them together. And unless you have both a quantum computer to break the old stuff and a mathematician who broke the new stuff, you're not breaking the connection. Great. So CryptoTLS can now negotiate that with Chrome and can negotiate that with other Go 124 plus applications. Not only that, we also removed any choice you had in ordering of key exchanges, because we think we know better than you, and that didn't come out right. But because we assume that you actually want us to make those kind of decisions, so as long as you don't turn it off, we will default to post-quantum. You can still turn it off, but as long as you don't turn it off, we'll default to the post-quantum stuff to keep your connection safe from the future. Same stuff with SSH. Starting in 038, they have the same thing. They just put them in a different order, which you would think doesn't matter and doesn't matter, but there are rules where no, you have to put that one first. And the other rule says, no, you have to put that one first. It's been a whole thing. I'm tired. Anyway. But yes, SSH, same thing. OpenSSH supports that, so if you connect to a recent enough version of OpenSSH, that connection is post-quantum, and you didn't have to do anything except update. Great. But then somebody asked me, okay, but you said key exchanges and digital signatures are broken. So what about the other ones? Well, key exchanges are urgent because of the recording problem. But unless the physicists that are developing quantum computers also develop a time machine, they can't use it to go back in time and use a fake signature today. So if you're verifying a signature today, I promise you it's not broken by a quantum computer. So we have a lot more time to figure out post-quantum digital signatures. But if we can, why should we not start now? Well, it's different. Key exchange, we knew what hit we had to take. You have to do a key exchange, you have to do it when you start the connection, and this is what we have, so we're going to do it. Signatures, we developed a lot of protocols like TLS, SSH, back when it was a lot cheaper to put signatures on the wire. So when you connect to a website right now, you get 5 signatures. We can't send you 5 2-kilobyte blobs every time you connect to a website. So we are waiting to give time to protocols to evolve, to redesign things with the new trade-offs in mind of signatures are not cheap. So we are kind of slow rolling intentionally the digital signature side because it's both not as urgent and not as ready to deploy to everything. I can't do the same thing of, ta-da, it's solved for you, because signatures are much harder to roll out. All right, so that was post-quantum. Let's talk about another thing that I had mentioned last year, which is FIPS 140. FIPS 140 is a US government regulation that regulates anything you do with cryptography when you are selling into a regulated market. And it is a list of algorithms, but it's not just a list of algorithms. It's also a list of rules that the modules have to follow. What is a module? Well, a module used to be a thing you would rack. And all of the rules are based on the idea that it's a thing you can rack. And then you can say, the auditor can ask, where does the module start and end? And you're like, it starts over here and it ends over here. And then, you know, that works. When people ask those questions of libraries, I do get a little mad every time. Like, what are the data input ports of your library? Ports. Okay. Anyway, it's an interesting thing to work with. But up to now, to do that with Go, you had to use unsupported. Somebody in this room needs to hear me. Unsupported Go experiment, which would replace all of the Go cryptography standard library, all of the stuff I'm excited about, with a boring crypto module, which is a FIPS 140 module developed by the boring SSL folks. And we love the boring SSL folks, but that means using CGO. And we do not love CGO because that has memory safety issues. It makes cross-compilation difficult. The list of algorithms and platforms is tailored to the needs of boring SSL and not to the needs of the Go community. And the development cycle of it doesn't match our development cycle. We don't decide when that module gets validated. Speaking of memory safety, I lied a little. Trail of Bits did find one vulnerability. They found it in Go plus boring crypto, which is unsupported, but they did find it in there, which was yet another reason to push away from it. So instead, we've got now the FIPS 143 Go cryptography module. It's native Go, but not just that, it's just a different name for the Go packages that all the Go cryptography uses for the FIPS 140 algorithms. So we just moved that into its own little bubble so that when they ask us, where does the module start and when does it end, we can point at the packages over there. And then there's a runtime mode, which does enable some of the self-tests and slow stuff that you need for compliance. It tells crypto-TLS not to negotiate stuff that's not FIPS. But aside from that, it doesn't change any behavior. So we managed to keep everything working exactly the same. You don't import a different package. You don't do anything different. Your applications just keep working the same way. And we're very happy about that. The final thing is that you can, at compile time, select a Go FIPS 140 frozen module, which is just a zip file of the source of the module as it was back when we submitted it, which is a compliance requirement sometimes. Which, by the way, means that we have to be forward compatible with future versions of Go, even for internal packages which we use, which was a little spicy. But anyway, now here's a problem. You might be surprised to find out that using a FIPS 140 algorithm from a FIPS 140 module is not actually enough to be FIPS 140 compliant. The FIPS 140 module also has to be tested for that specific algorithm. So what we did is we just tested them all. So you can use it not worrying about whether it's tested in our module. And when I say we tested them all, I mean that some of them we tested with 4 different names. Because NIST calls HKDF both SP800-133 section 6.3, SP800-108 feedback KDF, implementation guidance D.P one-step counter KDF. You don't want to know. It has 4 different names for the same thing. So we just tested it 4 times. It's on the certificate. You can use it whatever way you want, and it will be compliant. But that's not enough. Because even if you use a FIPS 140 algorithm from a FIPS 140 module that was tested for the algorithm is still not enough because it has to be tested on a platform that was tested as part of the validation. And so we tested on a lot of platforms. Some of them were paid for by various Fortune 100s that had an interest in them getting tested, but some of them had no sponsors. But we really wanted to solve this problem for everyone and for once and for all. So Jomis just paid for all of the FreeBSD, macOS, or even Windows testing so that we could say, run it on whatever, and it's probably going to be compliant. Don't quote me on that. How did we test on that many machines? Well, we have this sophisticated data center. No. No, I got a bunch of stuff shipped to my place. That's my NAS now. That's an Ampere Altra 6422, 64 cores of ARM64 machines. Yeah, that's my NAS. And then I tested it on, this sophisticated ARM64 macOS testing platform. And then on the Windows one, which was my girlfriend's laptop. And then the ARM one, which was my router. And then apparently I own an edge router now. It's sitting in the data center, which is totally not my kitchen. Yeah. Anyway, it was all a very serious and regimented thing. And all of this is actually recorded, like in recorded sessions with the accredited laboratories. So all of this is now on file with the US government. All right. So the easiest way, you might be surprised to hear that the easiest way to meet the FIPS 140 requirements is actually to not exceed them. And that's annoying and a problem of FIPS 140 in general, in the sense that if you do what everybody else does, which is just clearing the bar, nobody will ask questions. So sometimes in FIPS 140 mode, you just stake security a little lower. And we just refuse to accept that. Instead, we figured out complex concoctions where, for example, for randomness, the safest thing to do is to just take randomness from the kernel every time you need it. Because, for example, the kernel knows if a virtual machine was just cloned, and we don't know if it was cloned, and we risk just giving back the same answer twice. But NIST will not have that. You need to have a bunch of standards for how the randomness is generated. So what we do is that we do everything that NIST asks, and then every time you ask for randomness, we just like squirrel off, go to the kernel, get a little piece of extra entropy, steer it into the pot before giving back the result, and give back the result. And it's still NIST compliant because it's still as strong as both the NIST and the kernel solution. And same thing we did for ECDSA. So ECDSA is a digital signature mechanism. I've talked about it a few other times. It's just a way to take a message and a private key and generate a signature, here S and R. To make a signature, you also need a number, and that number must be used only once with the same private key. You cannot reuse it. That number is K here. Why can you not reuse it? Because if you reuse it, then you can do this fun algebra thing, and then plop, the private key falls out by just smashing two signatures together. Bad, really, really bad. So how do we generate this number that must never be the same? Well, one option is we make it random. But what if your random number generator breaks and generates twice the same random number? Well, that would be bad. So the community came up with deterministic ECDSA. So instead of generating at random, we are going to hash the message and the private key, and that will be my secret. This is still actually a little risky because if there's a fault in the SPU, for example, or a bug, because, for example, you're taking the wrong inputs, you might still end up generating the same value, but assigning a slightly different message because you didn't align things well. So how do we mitigate both of those? We do both. We take some randomness and the private key and the message, we hash them all together, and now it's really, really hard for the number to come out the same. And that's called hedged ECDSA. And the GoCrypto library has been doing hedged from way before it was called hedged and way before I was on the team. Except random ECDSA has always been FIPS. Deterministic ECDSA has been FIPS since a couple of years ago. Hedged ECDSA is technically not FIPS, but we really didn't want to make the thing less secure. So we found a draft that does a hedged ECDSA thing, and then we proceeded to argue that actually, if you read SP 890A revision 1 very carefully, you realize that if you claim that that's, the private key is just the entropy plus 2/3 of a nonce, that you are allowed to do because of SP 857 part 1, and we basically just figured out a way to claim it was fine, and the lab said, okay, shut up. So I'm very proud of that one. Anyway, if you want to read more about this, that's the announcement blog post. Well, that's the Geomis FIPS 140 commercial page. If you know you need commercial services for FIPS 140, if you don't know if you need them, you actually probably don't. So it's fine. The standard library will probably solve this for you now. Excellent. Okay, but who cares about this FIPS 140 stuff? Dude, you've been talking about FIPS 140 for 10 minutes, and I don't care about that. Well, I care because I spent my last year on it, and that apparently made me the top committer for the cycle to the Go repo, and that's mostly FIPS 140 stuff. I don't know how to feel about that. But also, we took care to make sure that everything that we found, we would leave in a better state. So there have been actually a lot of positive side effects from from the FIPS 140 effort. For example, there are new packages that moved from Xcrypto into the standard library. Crypto HKDF, Crypto PBKDF, Crypto SHA-3. SHA-3 is faster and doesn't allocate anymore. HKDF has a new generic API, which lets you pass in a function that returns either a concrete type that implements hash or a function that returns a hash interface, which otherwise was a little annoying. You had to make a little closure. I like it. Then we restructured Crypto AES and Crypto Cipher, and in the process merged a contribution from a community member that made AES-CTR, the counter mode, thing between 2 and 9 times faster. That was pretty good result. And the assembly interfaces are much more consistent now. And then we finished cleaning up Crypto RSA. If you remember from last year, we made the Crypto RSA sign and verify and so on operations not use mathbig and use constant time code. But now we also made key generation, validation, and pre-computation all not use mathbig. That made key generation much faster, made loading keys that were serialized to JSON a lot faster. Benchmarking key generation is really hard because it's basically a random process. Like you take a random number and you're like, is it prime? No. Toss. Is it prime? No. Toss. Is it prime? And you keep doing this. And if you're lucky, very fast. If you're unlucky, very slow. And if you want to average it out, you have to run it for hours. I think Russ tried to test it that way, and he ran for, what, an hour? A long time, exactly. So instead, figured out a whole new way by mathematically figuring out what is the average number of pools you are supposed to do, and preparing a synthetic run that gives exactly the expected mean number of tossings so that we get a representative sample to benchmark deterministically. That was a lot of fun. Anyway, we detect more broken keys, lots of good stuff, and we did a rare backwards compatibility break to stop supporting keys smaller than 1024 bits. Because 1024 is already pretty small, like you should be using 2000 minimum. But if you're using less than 1000, it can be broken on the proverbial laptop. So it's kind of silly that a production library lets you do something so insecure, and you can't tell them apart just by looking at the code. You have to know what the size of the key is. So we just took that out, I think. And I expected people to yell at me. Nobody yelled at me. Good job, community. Very good. All right, but aside from adding stuff, you know that we are very into testing, and that testing is how we keep that security track record that we talked about. So I have one bug in particular that is my white whale. And you might say, Filippo, well-adjusted people don't have white whales. And, well, we learned nothing new, have we? Exactly. So my white whale is this assembly bug that was there before I joined, that we found at Cloudflare, and that I spent like an afternoon figuring out an exploit for while in France, while the Yellow Jackets set fire to cop cars outside. That's a different story. It's an assembly bug where the carry, this is literally the carry, like when you do pen and paper multiplication, was just not accounted for correctly. And the problem with this stuff is that it's so hard to write code coverage for, because the code always all runs. It's just that you don't know if it always runs with that carry at 0. And yep, I added the carry and it's always 0. And if the carry is 1, it does the wrong math, but you don't know. So I think we've cracked it. And how we've cracked it is by using mutation testing. We have a framework that goes in there and tells the assembler, hey, anywhere you see an add with carry, replace it with a simple add that discards the carry. Then we run the tests. And if the tests still pass, well, the test did not cover that. And so we can fail a meta test and tell whoever's sending the CL, hey, no, you gotta test that. And same for checking the case in which the carry is always set. We replace it with add and then add one more. And it's a little tricky. If you want to read more about it, it's in that blog post. But I'm very hopeful that will help us with all of this assembly stuff. And next, accumulated test vectors. This is a little trick that I'm very, very fond of. And the idea is simply that you want to test a very large space. Like there are 2 inputs and they can both be 0 to 200 bytes long. And you want to test all of the sizes. Now that would be a lot of test vectors, right? If I checked in a megabyte of test vectors every time I want to do that, people eventually would yell at me. So instead, what we do is that we run each size and we take the result and we put it inside a hash. A rolling hash. And then at the end, we take the hash result and we check that it comes out right. We do this with 2 implementations. For example, that's why you're looking at Python. And if it comes out to the same hash, great. If it comes out not to the same hash, yeah, it doesn't help you figure out what the bug is. But it tells you there's a bug, so hey, I'll take it. And then more test suites. We really like reusing other people's tests. We're lazy. So the boring SSL people have a fantastic suite of tests for TLS called the BOGO. And Daniel has been doing fantastic work integrating that and making crypto TLS stricter and stricter in the process. So it's now much more spec compliant on the little things where it goes like, no, you're not allowed to put a 0 here. It has to be, it's very good. And then the Let's Encrypt people have a test a suite for the Acme protocol called Pebble, because it's a small version of their production system called Boulder. It took me a long time to figure it out. Like, eventually I was like, and finally, NIST has this public key interoperability test suite, which just doesn't have a good name. It's good though. Right, then more assembly cleanups. There used to be places in assembly where, as if assembly was not complicated enough, it was just written in machine code. It was just like, here's the encoding of the instruction, like, gee, thanks. And then comment, which sometimes is wrong. Can you tell the comment changed in that patch? This is a thing that Roland and Joel found, like, oh, okay. And now there's a test that will just yell at you if you put back a word or byte instruction in there. And we also removed all of the assembly that was specifically for speeding up stuff on CPUs that don't have AVX2, because AVX2 came out in 2015, and if you want to go fast, you're probably not using a CPU generation from back then. We still run on it, just not as fast. And then more landings. Okay, so I'm going to speed through these ones, but this is all stuff that we talked about also last year and that we actually landed. So stuff like data-independent timing to tell the CPU, no, I actually didn't mean for you to do that in constant time, goddammit. And server-side TLS encrypted client hello, which is a privacy improvement. We had client-side, now we have server-side. Crypto rand read never fails. We promised that. We did that. Now, do you know how hard it is to test the failure case of something that never fails at the kernel level? I had to re-implement the seccomp library to tell the kernel to break the get random syscall to check what happens when that happens. And then there's another test that when that test doesn't run, it makes sure that they're all pointing guns at each other to make sure that if anybody moves by an inch, we break, because I'm so scared of that code. And it's also much faster now because Jason Donenfeld added the Linux vDSO get random. Shan Liao, I hope that's the right pronunciation, added run text like we promised. And then more stuff like hash cloner, which I think makes a lot of things a little easier, and more and more and more and more. And the release notes are there for you. Xcrypt SSH is under our maintenance, and some excellent stuff happened there too. Better tests, better error messages, better compatibility, and we're working on some V2 APIs, which if you have opinions, it's time to come to those issues to talk about. All right, so that's been an exciting year, and I'm going to give you just two samples of things we're planning to do for the next year. One is TLS profiles. Approximately no one wants to specifically configure the 15 different knobs of a TLS library. Approximately no one, because I know that there's some people and they yell at me regularly, but instead most people just want, hey, make it broadly compatible, hey, make it FIPS compliant, hey, make it modern. And so we're looking for a way to make it easy to just say what your goal is, and then we do all of the configuration for you in a way that makes sense and that evolves with time. I'm excited about this one. And maybe something with passkeys. If you run websites that authenticate users a bunch with password hashes and maybe also with WebOSN, find me, email us. We want feedback. We want to figure out what to build here into the standard library. All right, so it's been a year of cryptography, but it's also been a year of GeoMIS. GeoMIS launched a year ago here at GopherCon. And if you want an update, I went on the Fall Through podcast to talk about it, so check that out. And we are now a real company, and how you know is that we have totes. It's the equivalent of a Facebook official relationship. But the best FIPS 140 side effect has been that we have a new maintainer. Daniel McCartney joined us to help with the FIPS effort, and then we are working very well together. So GeoMIS decided to just take him on as a permanent maintainer on the GoCrypto maintenance team, and I'm very excited about that. This is all possible thanks to our clients, and if you have any questions, those are the links. Thank you.